Welcome everyone to the next lesson in this series, and in this video we will look at Node-Local DNS cache for Kubernetes. Now, in one of the previous lessons we looked at how DNS works under the hood in a cluster, and typically you would have all the pods in the cluster sending DNS queries to the kube-DNS service, and this service can be backed by several CoreDNS pods or endpoints in the cluster. Now, as your cluster grows, you can also scale the number of CoreDNS pods, but this architecture may run into limitations in certain scenarios. If you have workloads that's sending a large number of DNS queries per second, or if you've got large scale clusters with a high density of workloads, you may experience DNS latencies, timeouts, or retries. Now, in this setup, the pod that initiates the DNS query and the CoreDNS pods will most likely be in different nodes in the cluster. And depending on the architecture of your cluster and the network that backs it, this could add to the end-to-end latency of a DNS query. Next, a common issue with this setup is to do with the contract table. Now, if you look at this connection, the pod initiates a DNS query which hits the kubeDNS cluster IP service, and the packet gets destination NATed to the CoreDNS pod IP address. So a contract entry gets created for the DNAT as well as the UDP packets. Now, when you have a large number of pods, and if those pods have a very bursty DNS behavior, and this could even be in scenarios where you're bringing up an application or repaving your nodes, where suddenly you have a large number of pods coming up and they're starting to send DNS queries, this could exhaust the contract table. And if the contract table fills up, you're going to experience DNS timeouts, delays, and latencies. Additionally, as the node contends for all these connections, it has to maintain a kernel state for those connections, and you may experience race conditions there as well, which can lead to DNS issues. Now, these issues tend to get further compounded by the fact that all these pods are going to retry their DNS queries. So you're going to see a DNS storm-like scenario. So something definitely to watch out for. Now, one of the other benefits of having Node-Local DNS cache is that it forces DNS queries to use the TCP protocol. So unlike the default UDP queries, which have a timeout of about 30 seconds, TCP connections are immediately removed from the contract table as soon as the connection is closed, and that frees up space in the contract table. Now, I've listed some other benefits of Node-Local DNS as well, so you can read the lab guide for that. Next, let's look at how Node-Local DNS cache works under the hood. All right, so in a Node-Local DNS cache setup, every node in the cluster will have what is known as a local DNS cache pod that gets deployed as a daemon set. And when a client sends a DNS request to the kubeDNS service, that traffic will be intercepted and redirected to the local DNS cache pod. Now, if this pod has that DNS request in its cache, it's going to respond back to the client without querying the CoreDNS pods in the cluster. However, if it doesn't have that request in its cache, it's going to send a DNS query in TCP and pass the response back to the client pod, and it'll maintain that in the cache depending on how you've configured the cache duration. Now, although this setup looks simple, there are some nuances to this. I've seen engineers fumble around this. So in this lab, we will be exploring this end-to-end flow in much more detail. So let's get started. All right, so this lab is lab number 17. You can find the lab in folder 17-node-local-DNS cache. I have already gone ahead and deployed my lab. And once done, you can export the kubeconfig file and do a kubectl get nodes. This should make sure your lab is running. So this is a 3-node lab. And if I do a kubectl get pods for the kube-DNS pods, we see that we have 2 pods in this lab. Now, if you do a kubectl get services for the kubeDNS service, we see that the cluster IP is 10.96.0.10, and we've looked at this in the DNS lesson as well. Now, if you look at the resolve file in a pod in the cluster, you can see that it's pointing to 10.96.0.10 as its name server, which is the IP address of the kube-DNS service, right? All right, so next, let's go ahead and deploy Node-Local DNS in this cluster. I've given the link to the official Kubernetes documentation as well as a link from which you can download the Node-Local DNS manifest. In this lab, it is provided. So I'm going to copy it to the root directory. And before you apply this manifest, there are some variables that have to be defined. So let's go through them one by one. The first variable is local DNS. Now, you can provide the Node-Local DNS pod a local IP address as well from the link local IP address space. And the idea behind this is you can configure kubelet to configure the name servers of the pods to point to this link local address. But one of the challenges with this method is that I've seen users deploy Node-Local DNS in clusters that are already live, in which case you already have pods that are pointing to the cluster IP of the kube-DNS service as their name servers. So in this lab, we will look at how you can intercept that traffic and redirect it to the Node-Local DNS cache pod. Okay, but you can still go ahead and specify this value, and you could make those adjustments for new pods that could be deployed in the cluster. Now, the second variable here is DNS domain. This is typically cluster.local, but you could have a different domain in your cluster as well. So make sure you populate the value with the domain of your cluster. And the third variable is DNS server, which is basically the IP address, the cluster IP address of the kube DNS service. And there are a couple of other variables that the Node-Local DNS pods will pick up from the cluster as they are deployed. I will cover these variables subsequently. Okay. All right. So next, let's go ahead and define these variables for our cluster. The first one is the cluster IP service of the kube DNS service. And the second one is the domain name. And the third one is the link local address for the Node-Local DNS pod. Now, with those variables defined, I am going to now replace those values in the Node-Local DNS manifest. Okay. And once done, let's go ahead and apply the manifest. And that's pretty much it. That creates Node-Local DNS in your cluster. And it does all the underlying networking magic. And believe it or not, your pods are now relying on Node-Local DNS for DNS resolution. But the trick here is understanding how this works under the hood. Okay. So with that deployed, if you do a kubectl and get pods, you can see we currently have 3 Node-Local DNS pods running in this cluster. This is a 3-node cluster. So currently they are present in all of the nodes. Okay, so as part of the manifest we deployed, we created this service called kubedns-upstreams. If you do a kubectl get services, you will be able to see this kubedns upstream service. I'll explain why this additional service is required shortly. Okay. Now, next, as you deploy the Node-Local DNS pods, these pods are going to be doing some underlying changes to the networking and routing functions of all the nodes in the cluster. And next, let's look at what those changes are. All right. So first of all, let's run this command to grab a cluster node. And if I echo the cluster node, this is worker 1, and this is also a node in which I have a DNS-test pod running that we will use to test some of the settings here. Now, if you look at the interfaces in this node, there's going to be a new interface called Node-Local DNS. And if you look at the IP addresses of this interface, it has, first of all, the link local IP address that we defined as part of the manifest we applied. And secondly, it also has an IP address of 1096.0.10. Remember, this is the cluster IP of the kube DNS service. So it's gone ahead and configured the IP in this Node-Local DNS interface. And you're going to find this interface configured in all the nodes in the cluster. Now, in this cluster, I have a pod called DNS-test. And this pod is deployed in worker 1. Do dash wide. As you can see, it's deployed in worker 1, right? And next, we're going to look at the resolve.conf file for this pod, and there are no changes to this file. And let's confirm that this pod is still able to perform DNS lookups, and it is able to do so. So as far as the pod is concerned, all these changes are going to be transparent. Okay, so you could roll this out without impacting the existing pods deployed in your clusters. Okay, so I'm going to bring up another diagram to explain this setup. So the DNS test pod from which we ran the query is still sending it to the IP address of the kube-DNS service. Now this traffic gets redirected to the Node-Local DNS pod on that node. And let's look at how that redirection happens. Okay, so next we're going to look at some IP tables, and I'm going to go through this diagram very briefly. I'm not going to cover all the concepts in this diagram, but this diagram outlines the different chains that are present in IP tables. And when a pod sends a DNS query to the cluster IP of the kubeDNS service, that packet lands on the NAT table in the pre-routing chain. And in the NAT table, you're going to find rules that destination NATs that traffic to the IP address of the CoreDNS pods, right? This is the typical behavior, after which a forwarding decision is made and the packet is either routed to the destination pod if it's in the same node, or routed out the network interface if the pod is in a different node. Now, when you deploy Node-Local DNS cache, those pods are going to be configuring some rules in the raw table to untrack packets that are destined to the cluster IP of the kubeDNS service. Now, when the packets are untracked, contract is not going to track it, and as a result, they do not get destination natted. So the packet exits the pre-routing chain with the destination IP of the cluster IP 1096.0.10 in our example. And if you remember, that IP now is locally present in the Node-Local DNS interface. As such, the packet enters the input chain and is redirected to that local interface or the local process, right? So next, let's look at the changes or the IP table rules that are added to the raw table by the Node-Local DNS pods. Okay, so let's look at the IP table rules that the Node-Local DNS pods configure in the raw table. Now, the lab already comes with K9s deployed. So if you type K9s in the terminal, you'll be able to get into K9s. I am going to navigate to the kube-system namespace and go into one of the Node-Local DNS pods and press L to look at the logs in the pod. Now, the logs that we are interested in are the IP table rules configured in the raw table in the pre-routing chain. As you can see, this rule basically specifies that any traffic destined to this IP, which is the linked local IP address that was configured for the Node-Local DNS pods, we're going to be skipping contract. Similarly, you can find rules for the kubeDNS cluster IP as well, so 1096.0.10. So any traffic destined to these IPs on port 53, TCP or UDP, we will be skipping contract, right? So what this means is the packet will exit the pre-routing chain while still retaining its destination IP. Now, the pod is also going to be configuring some rules in the filter table of the input chain to basically accept the traffic, right? So if you remember the diagram we looked at previously, this is the filter table of the input chain. So as the packet comes out, it has configured rules to accept the packet and forward it to the local interface or the local process, right? Now you can validate the changes that I've made to the IP tables of a given node by running IP table commands. As an example, these are the changes made to the pre-routing chain in worker 1 as an example. Now you see some similar rules in the output chain as well, and that's to make sure that the responses that are initiated by the Node-Local DNS, the local process, is not tracked in contract as well, right? So basically, any requests and responses going into Node-Local DNS is not tracked by contract, and as a result, it does not utilize the contract table, getting rid of all the contract issues we spoke about previously. All right, so we have all of that happening under the hood. Next, let's run some commands to verify that DNS is in fact being served by the Node-Local DNS pods. So in this cluster, we have a pod called DNS-test. I'm going to run some commands to identify where that pod is scheduled. It's scheduled on worker 1. And we will also next find the Node-Local DNS pod on that worker. This is the name of that Node-Local DNS pod. And I am next going to set up a port forward to that pod. Okay. So with that port forward running, we can run some commands to get some metrics from that pod. Now let me clear this. Okay, so once we are able to retrieve those metrics, let's run some commands to look at the hits to the DNS cache. So right now I have about 4 hits. I'm going to do a few more DNS lookups, right? And next, if I look at the hits, I have 7 hits now for the 3 DNS lookups that I did. So as I do more and more lookups, those are being served by the Node-Local DNS cache. Now, if you want to identify the number of entries that are currently being cached, you could run this command. And in my case, I have a single success entry and 3 denial entries that are currently being cached. And I'll explain what these denial entries are shortly. Okay. So just a few more times, let's clear and run some DNS lookups. And if I look at the hits, you can see them increasing. And this means that DNS is in fact being served by the Node-Local DNS cache. All right, so let's look at what those denial hits were. I'm going to run this command, which basically grips for hits, misses, and requests. Let's go ahead and do that. Just bear these numbers in mind. So in terms of cache hits denial, it's 14. Cache hits success, 12. Cache misses, 31. So these requests get sent to the CoreDNS pod or the kubeDNS service. And the total is 57, basically the aggregate of the 3. And I am going to now run another DNS lookup from the DNS-test pod to the Kubernetes service. And let's look at those values again. So in terms of the cache hits, they are the same, 14 and 12, right? However, the cache misses have increased by 3. I just ran a single DNS lookup and the cache misses have increased by 3. Let's do another DNS lookup and look at those metrics again. And this time I have the success hits increased by 1 from 12 to 13, and the cache misses have increased by 236. Okay. So what are these cache misses? Now in Kubernetes, although I'm running a single query, the pod resolver is going to take that query and append search suffixes and generate multiple DNS requests. So if you look at the resolve.conf file of the pod, which is this one over here, you can see the search suffixes. So we've got 1, 2, 3, 4 search suffixes. However, we have an n-dots configuration of 5, which means a DNS query can have up to a maximum of 5 dots. And if you look at the query that I'm sending, kubernetes.default, it already has 1 dot. And if the resolver is to append search suffixes, it has to append another dot and then include the search suffix. So it's going to be sending these queries out by appending these suffixes, and it'll stop once it has received a successful response. So you really cannot know how many invalid queries are made. But bear in mind that a single DNS query generates multiple queries towards the DNS server. And the reason for this is so that you can query service names by using short names instead of FQDNs in a Kubernetes cluster. Now, this can be problematic because what's happening is although we are responding to DNS queries using the cache, we are not caching the denial entries as much as we'd like to. As a result, for those DNS queries, the Node-Local DNS cache has to query the CoreDNS pods and try to get a response, which is basically an unnecessary amount of DNS queries going towards the CoreDNS pods. Now, there are several ways to address this. What we will be doing in this lab is exploring the config map in the Node-Local DNS cache, and you can make some adjustments to the DNS records that would be cached, the denial DNS records that would be cached, right? So if you look at the config map for successful DNS responses, we are caching the records for 30 seconds. However, for denials, we are only doing so for 5 seconds. So as a quick test, what I can do is let me increase both these cache values to 60, right? Let me save that. And once done, I'm just going to restart the Node-Local DNS pods. Let me clear all of this and let's run some of those queries again. So first off, all right, so I need to reinitiate the port forward because my pod names have changed now. So let me get the pod in worker one and reinitiate that port forward. And once done, let me clear that. And I am going to now initiate some DNS lookups. And let's get those metrics one more time. Let's just give it a minute. It's going to take some time here. All right, I just had to run some DNS queries and I was able to now get those metrics. So I have 6, 3, 3, and 12, right? So 12 is the total. So in terms of denials, I have 6, success 3, and in terms of misses, I have 3. I'm going to run, let me get the output one more time, and let me run a DNS lookup, and let's get that output again. So in terms of misses, it's still 3, right? Denial has increased by 2 and success by 1, okay? And after a few seconds, I am going to try that again. And I'm guessing that, both the caches expired at this point, and let me try that again now. Okay, so as you can see, the misses are still 6. I'm going to try that again. Misses are still 6, and I can see the success hits increasing as well as the denial hits increasing. Let's try that again. Misses are still 6. So as you can see, all these DNS, so now the misses went to 9, which means the cache entry expired. And if I do the lookup again, you can see that it's still at 9. And these responses are being served by the Node-Local DNS, right? So that's the logic behind this, behind how it's going to cache those DNS records. Of course, in this cluster, we have a single pod, but consider a scenario where you have pods in the hundreds in a given node, right? In high density clusters. In those cases, that's where you really see the benefit of the Node-Local DNS cache, all right? So what I'm going to do next is let me put those values back to their defaults. These are some parameters that you can tune for your clusters. So just bear those in mind. And the default values were 30 and 5. Okay. All right. Now, next up, what we're going to do is we are going to add some logging to the core file. And the idea behind this is that we will be able to see the name lookups being served by the Node-Local DNS cache. So I am going to go ahead and add these, modify this config map and add the log line, okay, in these to the core file. So let me go ahead and do that. All right, so I went ahead and added the log line, and I am going to save this config map and initiate another restart of the Node-Local DNS pods. All right, so let's clear this. Okay, so let's get the name of the node and now the name of the pod after it restarted. All right, so with that, what I can do is I can look at the logs in the pod after we modified the config map, right? So we can see logs in the pod here. And let's initiate a few more DNS queries, right? So one to kubernetes.default and one to google.com. And let's look at those logs. Let me rerun those queries. And if I look at the logs, I can see that these were served by the Node-Local DNS. So for example, google.com as well as kubernetes.default.svc.cluster.local, right? And in production environments, you wouldn't want to have this type of logging. It can generate a significant amount of logs, but for the lab, this is another way in which you can confirm that these are being served by the Node-Local DNS pod, okay? All right, so let me clear this. Let's go back to that config map. There's one more thing that I want to show you. Now, if you look at this config map, this is the field that basically forces the lookup to cluster DNS, the forward lookup, when there are no cache hits, to use TCP, right? So it says force TCP. And that way it ensures that, once the connection is closed, the contract entries are cleaned up as well. And there's one more thing about the Node-Local DNS. Now, if you look at the upstream servers, this the Node-Local DNS pod picks this up at runtime. And if you look at the pod, so let me just do a K9S, and let's go to one of those pods and look at the logs in the pod. And as this pod comes up, it configures the forward server as the host's resolve.conf file, right? And what that means is for DNS lookups that are not within the cluster, for external DNS lookups, the Node-Local DNS cache directly forwards that lookup to the host's resolver. And as such, this lookup does not traverse the CoreDNS pods, right? Now, this behavior may or may not be desirable, so you need to evaluate that for your environments. I know in certain production environments, they prefer that external lookups go through the CoreDNS pods, and that way you can control which name servers the CoreDNS pods are able to query by using things like network policies. And just to elaborate this a bit, so in this setup, for an example, like based on the parameters that was the configuration that we saw, for external lookups, the traffic gets redirected and the Node-Local DNS cache uses the host's resolver and forwards it to an external DNS server, right? It does not forward that to the CoreDNS pods. So you can configure the config map in such a way that those get forwarded as well, so that the CoreDNS pod is what does the external lookup, right? And that's based on the considerations you have to make for your clusters. Okay. All right, so that's it for this lesson. I hope you enjoyed it. It's definitely one of those tricky ones to understand all the moving parts behind how this works, but hopefully it was informative. Thanks for watching, and I'll see you in the next one. Bye for now.